from Normale Supérieur.
Because there are two microphones.
I switched
Yes. And Felix is going to tell us about large order summation of connected Feynman diagram for strongly correlated electron. So please, Felix.
Thank you very much, Sam, for the invitation to come over here after the March meeting.
Maybe we can just find a real pointer for you.
That would be nice.
Yeah.
Okay. So I'm Felix Werner from ENS Paris, and I will talk about work done with all of these people. In fact, it's two different works. Chris Van Hoek is my colleague at ENS. Nicolas Prokofiev and Boris Fissenov from UMass, École, Ricardo Rossi, who was our student, who is currently at EPFL, Gabriele Espada, who was our postdoc, and the group of Collège de France, Pedro Sinkovic from Hungary, and Michel Ferrer. And here is the list of papers corresponding to what I will present. Before starting, let me just spend a few seconds to think about the really tragic fact that war is back in Europe now. And as this lady reminds us, the nuclear bomb, which was built by physicists, can destroy mankind. Also, a more practical note, there is this letter which was written by Russian physicists abroad, which has been opened now to be signed by any physicists who want to sign it. So the general motivation is to develop unbiased approaches for fermionic and body problems, which are of course relevant in many areas of physics, where strongly interacting fermions play a key role, such as electrons in solids and molecules, nucleons in nuclear physics, or QCD. So a major theoretical challenge is to develop reliable and accurate predictions, to develop methods to do such reliable and accurate predictions, in particular for a large number of fermions and in the thermodynamic limit. So a sort of straightforward approach is to try to compute or to sample by Monte Carlo the wave function or the partition function, but this is actually very hard. For example, tensor network methods, which are developing a lot these days, are extremely successful in 1D, but in 2D it's much harder, and in 3D and in continuous space there is really not much at this point. And an older family of methods is what I would call bulk QNC, where the quantum problem in 2 dimensions in a finite volume L to the D is mapped onto a sort of classical problem with one extra dimension corresponding to the imaginary time, so that the volume is multiplied by beta. Beta is the inverse temperature. And this kind of mapping can be done in several ways. For example, using path integrals or auxiliary fields, or also what we call determinantal diagrammatic Monte Carlo. So in all these approaches, except in special cases, there is the so-called fermion sign problem, which leads to a CPU time that increases exponentially with the number of fermions. And in short, this comes from the following. When you want to compute quantity Q with such an approach, you will write it as a sort of average, but these weights here can change sign. And they can change sign very easily. For example, if we are interested in some observable which is localized in the center of the system, say the correlation function between 2 points within this finite volume, then if you have a small modification of your configuration C happening very far away, for example, with path integrals, if you have two fermions very far away which exchange with each other, then the sign of the weight will change. So this is very sensitive to what's going on very far away. However, usually we are interested in computing physical quantities which are local and which remain well defined even in the thermodynamic limit. So in some sense, this oversensitiveness of the representation to the sign is not really physical. And this is true even in presence of long-range order, provided you introduce an external field which you set to 0 after taking the thermodynamic limit. So to take advantage of this locality of the physics, we use the so-called diagrammatic Monte Carlo approach, but with connected diagrams, as opposed to the DDMC that I mentioned before. So the idea is very simple. Sum all connected Feynman diagrams up to a maximum order n max, and then increase n max and check that the truncation error goes to 0. So this works directly in the thermodynamic limit because we use connected diagrams. Here, the fermionic sign is actually helpful because it leads to a strong cancellation between diagrams, so that large order contributions are reduced, and on a lattice at finite temperature, the series are often convergent for fermions. Another advantage is the flexibility of the diagrammatic technique, which allows to change the starting point, or in other words, the order 0 of the expansion, and to reorganize the expansion, typically by using dressed propagators or vertices. And these two features make the approach non-perturbative. It's not anymore a simple expansion in powers of the bare interaction. And very often, the low orders are already a good approximation, which is why they are very widely used. And in that case, we are in a good position to compute the larger orders and hope to get convergence within what we can numerically reach.
Sorry, why is it called Monte Carlo? What, are you still sampling?
Because we are computing the diagrams using Monte Carlo.
So you're sampling among the diagrams?
Yes, I will mention it. So more formally, if you start from a physical problem that's described by some action S, the first step is to introduce a formal expansion parameter psi, such that when psi equals 0, so now the action depends on psi, in such a way that at psi equals 0, the action is quadratic. At psi equal 1, it reproduces the original physical action, and it should be an analytic function of psi. And then when you want to compute a physical quantity, which is a priori defined as some expectation value taken with the physical action S, then first you replace S with S psi, so that your physical quantity becomes psi dependent. And then you do the Taylor expansion in powers of psi. And we compute these coefficients using Monte Carlo, but that's just the technical aspect. And now the fundamental question is the following. Given this set of coefficients that we can compute up to a large order, let's say mathematically up to an infinite order, can we, from these coefficients, obtain the value of the function q at psi equal 1, which is the physical quantity q that we are interested in? So in the simplest case, the series is just convergent, and then the answer is yes, and we just need to sum up these coefficients. However, even if the series diverges, we can still obtain the value of the function at psi equal 1 using resummation methods, provided the function is resummable. So let's look a bit at these different situations in the complex psi plane. So this is the physical point, psi equal 1. And typically, the function q of psi will have some singularities in the complex plane, which often corresponds to zeros of the partition function. So it can be some isolated singularities or some branch cuts. And the convergence radius of this series will be given by the singularity which is closest to the origin. If this distance is bigger than 1, so if 1 is inside the convergence radius, then we are in this situation, the series converges, and we just need to sum up the coefficients to get the value of the function at 1. If there is some singularity which is closer to the origin, a distance smaller than 1 from the origin, so the convergence radius is smaller than 1, then we are in this situation, and provided there is no singularity or branch cut between 0 and 1, it's pretty easy, at least on paper, to resum the series using, for example, a conformal mapping. A more tricky situation is when we have a singularity at the origin, and I will discuss such an example later.
Isn't that the generic situation in quantum field theory?
So as I mentioned, for fermions on a lattice, typically the series have a finite convergence radius. But indeed, in the continuum, it's probably generically like that. So how do we compute these coefficients? They are typically the sum of all order n connected Feynman diagrams. So, for example, if Q is the density, then this is an example of a third order diagram. This is the external point. Here we have internal vertices, which are, let's say, in the representation position imaginary time. Tau is imaginary time that runs from 0 to beta. And we have to integrate over these internal variables and sum over all possible connected topologies. And the integrand will be a product of these propagators. And because the diagram is connected, this goes to 0 when any vertex is taken to infinity. So that's why this quantity is well defined for the infinite volume. So in order to compute efficiently such quantities at a pretty large order, several kinds of Monte Carlo algorithms have been developed and used. The first kind was proposed by Prokofiev and Svistunov, and first developed for the Hubbard model around 2010. And there, a configuration of the Monte Carlo process is defined by the set of internal variables and a given topology, capital tau. And the probability for the Markov process is just proportional to the absolute value of the product of propagators. More recently, Riccardo Rossi introduced another kind of algorithm that we call CDET for connected determinant, where a configuration is just defined by the set of internal variables, and the sum over all topologies is done exactly with machine accuracy at each Monte Carlo step. And the weight of a given configuration is just the absolute value of this. There is also another kind of algorithm which is sometimes called cluster diagram C, where it's somewhat similar to CDAT, but it's in momentum space. And there it actually matters to find a smart way of, this labeling of the lines by momenta is not unique, and it matters to find a smart way to do this labeling. So let me concentrate on these two algorithms for simplicity. And let me quickly discuss their computational complexity. The CPU time at order n scales like n factorial squared for diagram C, because the number of diagrams increases factorially, and it increases only exponentially for CDAT. I will describe later how it works. So in any case, it's expensive to compute high orders. But on the other hand, if the series is convergent, then you don't really need to go to very high order in order to get an accurate result. So the net result is that for CDAT, the CPU time, in order to reach a certain accuracy epsilon, which is given by the statistical error plus the truncation error, the CPU time only increases like a power law.
So you're computing loops,
Yes?
not diagrams with legs, not correlation function, but just loops.
No, we can compute correlation functions as well.
I see. Sorry. So I have a question.
Yeah.
If loops, then the result will depend on coupling constant and temperature and size of the bonds, right?
Yes.
So it's very limited information. If legs, then it will depend on momentum which enters the diagram.
Yes.
Which have entirely different physics, whether it's momentum small, large, what's the relation between. So all asymptotes are different.
Yes.
And you can do all these kind of things.
Yes. Yeah, I will show an example at the end where, for example, we compute the momentum distribution. So as a function of momentum.
But if there are, say, 4 legs, it will be a function of 4 variables.
Yes.
Which has entirely different asymptotes, because physics is different with a ultraviolet relation between these momentum is very different.
In principle, it's not a problem to have a larger number of legs of external variables.
Mm-hmm.
The only problem, of course, is that if you want to store this in memory for all possible values, then you might have a problem.
Yes, and it's impossible to analyze it. Probably convergence is very different depending on the value, on the relation between entering momentum. So
I don't think so.
Because convergent diagram, this complex plane of particles, which showed.
Yes.
This is for partition function.
No, it's the singularities are typically the same for any quantity. For the free energy. So it's important to take the log of the partition function. If you just take the partition function, then you cannot work in the thermodynamic limit. So on the one hand, if you just do the partition function, it will typically always converge for a finite volume. But on the other hand, you cannot take the thermodynamic limits. So we are not interested in that.
So you assume that the order of limits. You must assume some order of limits, right? You have lattice, you have you have n, the order.
Yeah.
Diagram,
so the order of limits usually it doesn't matter, but in the broken symmetry phase it matters, as I will explain. So with these approaches for lattice models, in the last decade, many results have been obtained. Here I mention some of them. I guess I will not have time to go through the list. So repulsive Hubbard model in 2D or also in 3D. So very recently they observed incommensurate correlations in 2D and also phase transition to an incommensurate phase in 3D. There was also a lot of papers by Tupitsin and Prokofiev about different models. Also Johan Karlström from Stockholm. So there was also works on frustrated spins, which can be mapped to fermions. So all of these works are in normal phases. There is just one paper about topological phases with magnetic order. So here I will present some results for a superfluid phase or superconducting if you prefer. So this will be the first part of the talk about high-order diagrammatic expansion around BCS Hamiltonians and application to the polarized superfluid phase of the attractive Hubbard model. So the Hubbard model on a 3D cubic lattice, the Hamiltonian has a kinetic part which corresponds to the hopping between nearest neighbor sites, chemical potentials mu up and mu down, which depend on the spin, and an interaction part, which is the on-site interaction, which we take here attractive. How do we set up the diagrammatic expansion in the superfluid phase? So it's the S-wave superfluid phase where the order parameter is this quantity, C up, C down on the same side. So we use an unperturbed quadratic Hamiltonian, H0, which is the original kinetic part, some chemical potentials which can be different from the physical ones, that's a standard technical trick. And most importantly, we add a symmetry breaking term here, which breaks U1 symmetry, which has the standard form of a BCS Hamiltonian with some prefactor delta naught. Then we introduce the formal expansion parameter xi and define h xi as a linear interpolation between h0 when xi equals 0 and the original h when xi equals 1. Then we follow the standard procedure that I introduced before. So when we want to compute some quantity q, we evaluate it formally with h xi so that q becomes xi dependent, and then we expand in powers of xi. And here we will see that actually we are in this case where the series converges. So we just need to sum up these coefficients.
I have a question. So when you add this breaking U1 term, do you have a problem with the gain invariant when you can use the correlator?
Problem with the
gain invariant, the U1 invariant when you have the correlator, when you can make the correlator.
I don't see which problems you are talking about.
So if you add the breaking U1 symmetry operator term like explicitly in your Hamiltonian.
Your Hamiltonian has a symmetry when
Can we discuss it later? Maybe I will answer the question. I'm not sure that
your Hamiltonian has a symmetry when xi is equal to 1.
Yeah.
Which is number conservation, but not for any other value of xi. I think that's the question. Is that an issue for?
No, on the contrary, it's exactly what we need. So I think I will come back to it later. I will ask again if you will get it. So we will also be interested in the pressure, which is the free energy per unit volume. The free energy is of course the log of the partition function. So here, in order to make it xi dependent, we just replace h with h xi and then expand in powers of xi. And we compute these coefficients, which will be fully closed diagrams. And again, the series will just converge. So note that in h xi, we have a symmetry breaking field, which is contained in h0. which is multiplied by 1 minus psi. So the symmetry breaking field is proportional to 1 minus psi. And let's take a look at the singularities as a function of psi in the different situations. So first, if we do not break the symmetry, so we take delta 0 equals 0, then typically if we are in the normal phase, there is no singularity between 0 and 1. And we are fine, we can get the result here by summing up the series, or if it diverges by resumming. However, if we are in the superfluid phase below TC, so the physical point here is in the superfluid phase, whereas here we are in the normal phase, and therefore we must have some singularity on the way. So in that case, it's usually not possible to obtain this result by resumming, because it's not possible to analytically continue through the singularity. Now, if we break the symmetry in H0, then if we are in the superfluid phase, there is no problem anymore, because it will be superfluid for any psi. Actually, as I will mention in the end, there is now a singularity at psi equal 1, but that's not a problem. So the order parameter as a function of psi now will have a finite limit at psi equal 1 when we switch off the symmetry breaking field. And this is the value of the order parameter that we are interested in. Let me also mention this case. If we break the symmetry, but we are in the normal phase, actually there is no problem either. Here there is no singularity either. The order parameter will just cross 0 at psi equal to 1. And we are everywhere in the normal phase, or we can call it para-superfluid, as in analogy with paramagnetic. So since we have here spontaneous symmetry breaking, as I mentioned, we should take the thermodynamic limit before switching off the symmetry breaking field. So when we compute the order parameter, these expansion coefficients should be evaluated in the thermodynamic limit, and only after that we should sum over orders. So regarding the choice of the parameters mu naught and delta naught of the unperturbed Hamiltonian, in principle we can choose anything. So in practice, we use a natural choice for mu naught, which is given by the Hartree mean field shift. And for delta naught, a natural choice is to use the value from BCS mean field theory. In other words, the value given by the gap equation. But sometimes we will also use the different values of delta naught. So just for illustration, here are some diagrams for the order parameter at order 0. This is the anomalous propagator. At order 1, but these guys actually cancel out each other if we take the mean field delta, because in that case, this counter term exactly cancels out the anomalous tadpole. Here is just for fun an example of the diagram of order 9. And in accordance with the general philosophy that I mentioned in the beginning, this is well defined in the thermodynamic limit, and the large distances will have a small contribution to the answer. And we are able to directly compute the order parameter in this way because we work in the broken symmetry point of view.
So in your previous graph, there is a singularity at c equals to 1.
Yes.
Is that because of Goldstone?
Yes.
Boson?
I will mention it in the end. So for the algorithm, we use the CDED algorithm now with number propagators. So this is the 2x2 matrix of number propagators with the normal propagators and anomalous propagators. And let me briefly mention how the CDED algorithm works without going into details. So if we want to compute the order parameter at order n, it will be given by an integral over the internal variables of some quantity, which we call CDEF of A. where A here is a matrix. It's basically the matrix of propagators which connect the different vertices to each other with these 2 by 2 number blocks. And C that is the determinant of this matrix minus something which corresponds to the disconnected diagrams and which can be computed recursively in 3 to the n operations. So that's why the CPU time only increases exponentially, even though the number of diagrams is factorial. And yeah, here are some details about the implementation. So let me show you some of our results. So we have chemical potentials mu up and mu down. Mu is the average chemical potential. H is the Zeeman field, the difference of chemical potentials. Hopping is set to 1, and we take the interaction strength U equal -5. We choose the average chemical potential mu to be some value such that the total number of particles per site is close to 0.5, so which is called quadrifilling. When the Zeeman field H is 0, that's one of the special cases where standard QMC methods are sign-free. So here are some data from the literature for the critical temperature at 0 Zeeman field as a function of the interaction strength. And you see that at U -5, we are clearly within the crossover regime between the weak coupling BCS limit and the strong coupling BEC limit. So first, we did some benchmark calculations at 0 Zeeman field where we can compare with standard methods. So here I show the order parameter at about 1/2 of the critical temperature. And this is the data for the series for delta close to the mean field value. So you see that we can reach order 12 loops, and the series looks convergent. And indeed, we can extrapolate it using standard methods to get a result with a small error bar. And then we compare to an established method, DDMC, which works for a finite volume. So for DDMC now, the results are not anymore as a function of maximum order. I mean, this was as a function of maximum order. But now for DDMC, it's as a function of L, the linear system size. And you see that in this case, the finite size effects are pretty small already at the accessible system sizes. And the result between the two methods agree very well.
Could you show the TC result? Do they sit bang on the standard answer as well?
We didn't compute TC in this work. Yeah. So now let me go to the polarized regime, non-zero Zeeman field, which means different chemical potentials between up and down, where no unbiased results are available due to the sign problem in standard QMC methods. So the expected phase diagram topology discarding FFLO is the following, based on BCS mean field and also DMFT. And it's also the same topology that was seen in Kodatom's experiments, but these experiments were actually not done for the Hubbard model, but in continuous space. So phase diagram as a function of temperature and Zeeman field. At small Zeeman field, you have the standard second order phase transition between superfluid and normal, but here the phase transition is expected to become first order. And at 0 temperature, the superfluid should remain unpolarized all the way up to the phase transition, simply because there is a gap. So let me show you some data for such a scan as a function of the Zeeman field at the temperature about 1/4 of TC. So in order to see the first order transition, we should compute the free energy. And on the one hand, we compute the free energy of the superfluid phase by breaking the symmetry. These are the blue points. And on the other hand, we compute the free energy of the normal phase by using delta 0 equals 0, so not breaking the symmetry, and these are the green points. And you see that indeed the two curves cross. Note that the superfluid phase is almost flat, which means that the magnetization density up minus density down is almost 0 as expected, according to what I said before, because we are at low temperature. So we can locate the phase transition point, and it's about 2 times smaller than the result from BCS mean field. This is the series for the free energy density, for the superfluid series, and for the normal series. So you see that the convergence is actually significantly better than for the other parameter that I showed before. And here we have checked that we are still, the other parameter is still non-zero, so we are still superfluid, but now we are in the metastable regime. So in the metastable regime, according to the general considerations I gave before, the series is supposed to diverge because now we should have a singularity between 0 and 1. But this divergence is slow if we are sufficiently near the transition point, because then there is a large energy barrier between the metastable phase and the stable phase, which corresponds to a weak singularity in the complex psi plane, which is a branch cut singularity of this type, and which leads to a large order behavior of the series, which for all practical purpose looks like a convergent series unless you go to very large order. So this is again the phase diagram. I've shown you the first order phase transition when we move along this line. And now let me show you some results at a higher temperature, where we will see that now there is a non-zero polarization of the superfluid phase. For this, we compute directly the magnetization, density up minus density down, again as a function of maximum diagram order. If we use the mean field delta, you see that the data does not show any sign of convergence up to the order that we can reach, which means that the mean field in this case is a very bad starting point. But if we tune a delta significantly away from the mean field, then the series look convergent. So in this way, we can claim a result for the magnetization, which corresponds to about 4% polarization. And the BCS mean field result, which is the order 0 here, is about 30 times smaller. So in this regime, we can use a simple quasi-particle description given by the usual effective Hamiltonian, which is just some free, non-interacting fermionic quasi-particles, which correspond to broken pairs. And based on general arguments, their dispersion relation, even though this function E sub k is unknown, should have a simple dependence on the Zeeman field H. And from this, we can evaluate the magnetization by this simple expression in terms of Fermi-Dirac distributions. Actually, the occupation numbers are small here, so we can replace them by Boltzmann factors. And then the dependence on H factors out. And the prefactor is the density of quasi-particles at the given temperature without Zeeman field. So if we then compute the magnetization for several values of H, we get this data, which are well fit by the simple formula from the previous slide, with one fitting parameter, which is this density of quasi-particles, which is very small, but clearly non-zero. And finally, the large order behavior of the superfluid expansion, which is an important fundamental question. Since the symmetry breaking field is proportional to 1 minus psi, we have actually here the square root singularity coming from the Goldstone mode, which is known in the literature. And the prefactor is also a known expression in terms of the superfluid stiffness. And if we do the Taylor expansion of the square root, we get a large order behavior, which is a power law for the order parameter and also for the pressure. So it's not very surprising that at large orders, even though the diagrams are local in a way, we start to probe large distances, which in this case are dominated by the thermal fluctuations of the Goldstone mode. So here are some data for the coefficients of the pressure as a function of order in a log-log scale. And you see that indeed it looks linear. So it looks like indeed a power law. Here you can have the impression that the exponent for the data is a bit different from the expected one. But actually by analyzing more closely, we see that our data is not sufficiently linear such that there would be really a discrepancy with this exponent. Moreover, the prefactor that we get by fitting the data is significantly larger than what is expected from this expression here if we take some DMFT results for the superfluid stiffness, which suggests that even though we reach order 13 here, we are not yet in the true large order behavior. In practice, it doesn't really matter because, as I showed before, the series for the pressure converges quite quickly. I mean, pressure is free energy density. So therefore, this is rather an academic question. Now, let me switch to another study that we have done in earlier years on the unitary Fermi gas, but in the normal phase so far. So the unitary Fermi gas, as many of you know, spin 1/2 fermions in 3D continuous space with interactions which have zero range and scattering length A equal infinity. So the notion of unitary Fermi gas is based on the following universality hypothesis. If you take any kind of interaction potential with a range B and infinite scattering length, which means that you have a two-body bound state at zero energy, and if you work in the zero range limit, meaning that the range B is small compared to the interparticle distance and also compared to the thermal wavelength lambda, then many properties of this system do not depend on the exact shape of the interaction potential. For example, in the unpolarized case, the equation of state, density as a function of temperature and chemical potential, multiplied by thermal wavelength cubed, so this is a dimensionless function. This is actually a universal function of beta mu. Beta is inverse temperature. This universal function can be computed directly in the zero range limit using the so-called zero range theory. So another way to define the unitary gas is to start from the Hubbard model, tune the interaction strength to this point, which corresponds to the zero energy resonance for the two-body problem. And then take the limit where the filling goes to zero, which corresponds to the continuum limit, naturally while keeping fixed T over Tf. So at the finite scattering length, you have the well-known BCS-BEC crossover between the weak coupling regime and the strong coupling regime where you have a molecular BEC. And the unitary gas is within the strongly correlated regime in between these two simple limits. There are cold atom experiments with fermionic atoms in two internal states near a Feshbach resonance, which are accurately described by the zero range model. So here is just a picture of an experiment at ENS. And qualitatively, this model is also relevant for neutron stars. So this problem has been extremely widely studied. There are many experimental groups, and the number of theorists is almost infinite. There are several of them in the audience. So diagrammatically, the standard first step is to use the so-called ladder summation, where you introduce this object gamma 0, which is basically a T matrix. It's the sum of the bare interaction vertex plus all of these particle-particle ladders. And this object is well defined in the continuum limit, which can therefore be taken analytically before we start doing any other calculations. We also use the standard notion of self-energy, which is related to the Green's function by the Dyson equation. And so in practice, we need to evaluate these diagrams, these one particle irreducible diagrams for the self-energy with this addressed interaction vertex. So in this work, we used actually the older diagram C kind of algorithm, and we could typically reach order 9, so 9 loops. And this setup, I will call it in what follows ladder scheme. Of course, we need to avoid double counting, so we should not allow these kind of structures. We will also use what we call bold scheme, which is a self-consistent scheme where the diagrams for the self-energy are now expressed in terms of the fully dressed G that I introduced before, and the fully dressed pair propagator gamma, which itself is expressed in terms of pair self-energy pi, which we also compute by Monte Carlo. So this procedure is repeated iteratively until convergence. So now we have to compute this quantity Q, which is sigma of pi. Again, we can formally expand it in Feynman diagrams. Let me call AN the sum of all order n diagrams. For example, A1 for the self-energy is this diagram, and A9 is this diagram plus about I think 100,000 others. And here we have a fundamental problem that the series has a zero convergence radius. So can we still obtain anything out of this series? So the solution is following the standard procedure, the procedure that I introduced before. So I'm sorry, here I will change the notations. What was called psi before, it will be called z here. So we can construct a function q of z such that, exactly like before, the Taylor expansion of q in powers of z has coefficients an, which are given by the diagrammatic series. And at z equal 1, we recover the physical quantity q. And now we need a resummation procedure to get the answer, which is q at z equal 1, taking as an input the values of the coefficients. So for this, in short, we use the instanton method to get a large order behavior and the position of the branch cuts in the complex z-plane. And then we construct an appropriate conformal Borel transformation, which can be shown to indeed lead the correct result based on a theorem by Nevan-Lina. So I don't really have time to present here in detail. Let me go very quickly. So in order to define q of z, we use a partition function, big Z of small z, which is a functional integral. Phi here are the original fermionic fields, while eta is a bosonic auxiliary field. And then if we formally integrate out the fermions, we get a bosonic action. So the original action, which has both the fermions and bosons, for the ladder scheme has a simple expression. As you can expect, you just have propagators for the fermions, and the propagator for the bosons is gamma 0. And then there is just a standard coupling between the bosons and the fermions. And this is a counter term which is needed to remove the forbidden diagrams. So coming back to this bosonic action, it can be evaluated by using a quasi-local approximation in the limit of a large bosonic field and small coupling constant. based on the instanton, which is the saddle point of this action. And the result is that there are two branch cut singularities in the complex Z-plane with this kind of essential singularity. And correspondingly, the large order behavior looks like this: n over 5 factorial times some exponential and oscillation of period 5. So based on this large order behavior that I write again here, the natural thing to do is this conformal Borel transformation. So first, the Borel transformation, where the coefficients are divided by this factorially divergent term, so that now this Borel transform has a finite convergence radius. It converges for z smaller than this a here. And then formally, the answer Q of 1 should be recovered by doing the inverse Borel transform, which is just given by this integral. So the question is whether this procedure is indeed mathematically correct. And we can argue that yes, it is based on the Nevanlinear theorem, which basically tells us that this holds provided the function is analytic within a domain which has this shape of a piece of cake. And also there should be a bound on the Taylor coefficients of the function, not only at the origin, but everywhere within the domain. And then after that, in practice, in order to evaluate this integral, because this function diverges if we are outside of the convergence radius, we use the standard procedure, which is to make a conformal mapping. In order to move the singularities outside of this disk, and now this integration domain here from Z from 0 to infinity is mapped within the convergence disk. So some results. First of all, for the equation of state, for example, at zero chemical potential, which corresponds to T over Tf about 0.6. So here are data for the density multiplied by thermal wavelength cube to make it dimensionless as a function of the maximal diagram order, and using the conformal Borel resummation. So you see that indeed the data converge, both for the ladder scheme in black and for the bold scheme in blue, and they agree with each other. And they also agree with the results from the MIT experiment. So here is a zoom, and you see that our precision in this case is better than 0.1%.
Could you explain
why, like, despite high precision, your answer seems to disagree with just the bounds from the experiment?
Oh, this is just an experimental error bar. It's not a strict bound.
I see, okay.
This is the same at lower temperature. When we start approaching the critical temperature, the critical temperature is about 0.16. So at this temperature, we cannot use the ladder scheme anymore. We only have the bold scheme, but we can use different variations of the conformal Borel, and we get these different curves which agree with each other and which still agree with the experiment. We also computed the so-called contact parameter, C, which determines the density correlation function at small distance. So for zero range interactions in 3D, it diverges like 1 over r squared with a prefactor, which is the contact. And it also determines the tail of the momentum distribution at large K. And it's also related to the derivative of the pressure with respect to 1 over A. So here we just can obtain the contact by evaluating the pair propagator at zero density and zero time. So essentially the contact is a density of pairs. So here are our data in blue. And shortly after our results, there have been 2 experiments in Australia and at MIT, which are in agreement with our data. And before our work, there has been lots of theoretical calculations. Here I show some of them. Finally, let me briefly discuss the momentum distribution. So here are our results for the momentum distributions for different temperatures. And of course, as we decrease the temperature, the distribution becomes sharper. So the slope at the Fermi momentum increases. So here I plot the inverse of the slope as a function of temperature. And if we extrapolate it to zero temperature, then we see that we clearly have a non-zero limit, which is in contrast to what we would get for a Fermi liquid. So you see that here this behavior is clearly not a Fermi liquid behavior. And finally, let me discuss why the contact as a function of temperature is so flat, even though here we have a broad range of temperatures, because note the scale here that this is really not a big temperature dependence. So this is the result of two competing effects. On the one hand, if we increase the temperature, so say we go from blue to red here, then of course we have larger occupations at large momentum. So therefore, in the curve of n of k times k to the 4, we will have a maximum which is higher at higher temperature. So I remind you that the contact corresponds to the large k limit of this quantity. So this effect tends to increase the contact at higher temperature. If the maximum is higher, then the plateau should be also higher. But on the other hand, the plateau also sets in at larger k when we increase the temperature. And this is simply because the condition to reach the plateau is that k should be not only large compared to kf, but also large compared to the thermal momentum. So as a result, we have these two competing effects, and in the end, they mostly cancel out each other. Also note that here in our data, we have no k-dependent Monte Carlo noise at large momentum in contrast to most other methods. And this is because the tail entirely comes from the lowest order diagram for the self-energy in the bold scheme. So what are the next steps for this approach? For the Harvard model, of course, it's also interesting to look at on the repulsive side, where the counterpart of what we have seen is the antiferromagnetic phase. And the Collège de France group is working on this. Also, it would be interesting to replace the bare vertex with ladders, as we have done for the unitary gas. And we know how to do it for seabed in the normal phase. And this would allow us to reach a stronger coupling, where it's expected that the superfluid phase can become polarized even at zero temperature. Also, it will be very interesting to look at potential FFNO phases, which, according to mean field theory, should actually have a lower free energy in large parts of the phase diagram. For repulsive U, this would correspond to stripe phases. And on paper, we just need in our H0 to use a position dependence delta 0 in order to study such phases. Also in 2 dimensions, it will be interesting to look in particular at finite temperature where we have the algebraic order, but maybe the same approach will still work. For D-wave superconducting phase, we should now use L delta 0, which depends on the relative momentum. For the unitary gas, in the normal phase, there are still many things to do for the polarized gas, also computing spectral functions. There are also new experimental data for Raman spectroscopy. In the superfluid phase, of course, a fundamental question is whether the series is still well resummable, like we have seen for the normal phase. And there is also an alternative approach that we have already tried, but we can maybe try more. which is called variational perturbation theory, and which has been used successfully for the electron gas. Thank you for your attention.
Can you do a little bit of doping of your Hubbard model to see if D wave turns on? Or is
Yes, absolutely. I mean, doping on the repulsive side is equivalent to polarization on the attractive side. So in this sense, what I've shown you was almost the same thing than doping on the repulsive side. The only difference is that here I took a density which was 1/2 particle per site. So if we want to map it to the repulsive Hubbard model unpolarized, we should take a density of 1 particle per site. But in fact, we have already done such calculations in order to compare with the repulsive code. I just didn't show them here.
I just had a nice question about your coefficient, the nk when k goes to infinity. So why isn't this sensitive to the microscopic realization? It seems like a very microscopic thing. Like, why should it agree with the experiment?
Because we have effectively zero range interactions. Of course, in the experiment, the range is not really zero, it's just very small.
Yeah.
So, which means that in fact, this tail will be cut off at some very large scale.
K is not too big, but bigger than.
Experimentally, yes.
But numerically as well, right? Because you also have some microscopic scale beyond which.
Yes, I mean, numerically, we always have some cutoffs. So I mean, the curve that I showed you here, I cannot continue it to infinity. But you see that it's already very flat. So.
And can you study dynamics, like transport, real-time observables?
So there are people who are doing dynamics within similar kind of approaches. There are many papers already on that. But so far, it was I think all the papers were for the Anderson impurity model. So doing it for say for the Hubbard model, it's a completely open problem. But I mean, of course, you can hope that it's possible by maybe by combining the equilibrium approaches that they talked about with the Keldysh approaches that people have developed for the Anderson impurity model.
I see. So they don't do imaginary time.
So another thing that I should mention, there has been also lots of papers in the last years about typically the Hubbard model or also the electron gas at equilibrium, but for real frequency. So typically they cannot reach the diagram orders which are as high as what can be done with the imaginary time, but still one can go to fairly high orders. And this is, I think, still a lot under development.
Can you study the problem to compute all the parameters?
Yes, I mean, we can, of course, break the symmetries in different ways and compare the free energies as similarly to what I have shown.
So basically, you consider the problem with one order parameter with another and compare the cell and compare the free energy.
Yes, and say if you are thinking about the repulsive Hubbard model, one can do either stripes breaking the translational symmetry, or D wave breaking the U1 symmetry, or one can also break both of them.
So when you do that, you have to start the perturbation theory around some ground state where that other parameter is put in.
Yes.
So can you improve your method for long-range regression?
Yes. So there has been already very successful works on the electron gas Coulomb interactions. So of course here it's crucial to screen the interaction. So actually here they use an unperturbed Hamiltonian or action, which includes a screened interaction.
Any other questions? Okay, if not, let's thank Felix again. Thank you. Very interesting. So FFLO in unitary, so unitary Fermi